In this video, we're going to look at topic 2.2 in Year 12 Chemistry, which is redox, rusting and iron. In reality, this topic is basically three smaller topics pushed into one. So we've got a section on redox, a section on rusting, and then a section on iron to look at. So the first section we'll look at is on redox. This section is basically about different words you can use to categorize different types of reaction. The main words we're going to use in this topic are oxidation, reduction and redox. And they can be used to describe or distinguish different types of reaction from each other. So the first thing we need to look at is the definitions of those words and what they actually mean. The first two words we'll look at are oxidation and reduction. Now the definitions for these are slightly unusual in that there's actually more than one definition for each. We've got 3 definitions for oxidation and 3 definitions for reduction. The reason we've got different definitions is that we can use these terms in different contexts. So it just depends on the particular reaction you're looking at. You can use one of these definitions to use the word oxidation or reduction. So for oxidation, we've got these 3 definitions. Oxidation is the gain of oxygen by an element, the loss of hydrogen by an element, or the loss of electrons by an element. Reduction essentially is the opposite of oxidation, which means that reduction is the loss of oxygen, the gain of hydrogen, or the gain of electrons. It's easiest to see how we use those definitions if we look at a couple of very simple examples, so I'll look at them just below. So we've got an equation here between magnesium and oxygen to make magnesium oxide. A question you could be asked about this equation in a test is whether this reaction shows oxidation or reduction. So how we would look at that is we would look at the magnesium at the start. We notice this magnesium by itself. At the end of the reaction, it's now magnesium oxide. That simply means that the magnesium has gained oxygen, and because oxidation is the gain of oxygen, the magnesium must have been oxidized. Now we have to be careful with how we express our answers in a question like that. It wouldn't be enough just to say that magnesium is oxidized. We have to back it up. And how we back it up is by using the definition for oxidation. So we'd say that oxidation is the gain of oxygen. Magnesium has gained oxygen, therefore magnesium is oxidized. Let's look at a second example. So for this next equation between copper oxide and hydrogen to make copper plus water, we could be asked the question, explain whether the copper is oxidized or reduced in this reaction. So if we look at it, we look at the copper at the start, it's joined to oxygen. At the end of the reaction, it's by itself, and therefore we can deduce that it must have lost the oxygen. We think back to our definitions, we look at that reduction is the loss of oxygen, therefore the copper must have been reduced. So once again we have to use that definition in our answer. We say that reduction is the loss of oxygen, the copper's lost oxygen, therefore the copper has been reduced. Two more words you can get asked about in a question are the words oxidizing agent and reducing agent, and you can be asked to identify these in a reaction. You have to be careful here. And the way I always imagine it is like the word or the term travel agent. If you go to a travel agent to get you on holiday, the travel agent allows you to travel. The travel agent themselves doesn't do the travelling. Same with these words oxidizing agent and reducing agent. An oxidizing agent is something that will oxidize something else. It doesn't get oxidized itself, it oxidizes another thing for it. Similarly, a reducing agent doesn't reduce itself, it reduces something else. So in this, for example, in the first equation, we look at the oxygen here. The oxygen has allowed the magnesium to be oxidized. Therefore, we'd say that the oxygen is the oxidizing agent. It's allowing something else to be oxidized. If we look at the second example, the hydrogen here has taken the oxygen away from the copper. Therefore, the hydrogen has allowed the copper to be reduced. And therefore, the hydrogen is the reducing agent. So there we have it. An oxidizing agent is a substance that oxidizes something else. A reducing agent is a substance that reduces something else. Now, one further term we can use to describe a reaction is in some reactions we see both oxidation and reduction happening together. The term we use to describe that kind of thing going on comes from the two words kind of joined together. We take the RED from reduction, we take the OX from oxidation, and we would call that a redox reaction. A redox reaction is when oxidation and reduction take place within the same reaction. Now I'm going to show you one last example of reaction that is a redox reaction, so we can look at this definition, and also an example where we are losing and gaining electrons, which is a more difficult style of redox equation to analyse. So we can look at this reaction here between magnesium and copper sulfate to make magnesium sulfate plus copper. This is an example of a displacement reaction from the reactivity series topic. And the question could ask you, in terms of electrons, explain why this is a redox reaction. So that'd be quite a difficult question. In terms of electrons, explain why this is a redox reaction. So let me just take you through the steps you'd need to do to work that one out. So the way this equation is written at the minute, it's very difficult to see if anything is gaining or losing electrons. So we have to do a step first of all, which is known as turning an equation into an ionic equation. Essentially, in this equation in front of us, we've always got like metals and non-metals, so all the compounds that we see are going to be ionic compounds. What we can do first of all is split them apart into separate ions and see what we can analyse from there. So here I've kept the elements the same, so magnesium is still magnesium, copper is still copper, but these compounds, because they're ionic, I've split them into their different ions, copper 2 plus and SO4 2 minus for sulfate, same for the magnesium compound. Now what I notice here is that of the ions in this equation, one ion doesn't change, and it's the sulfate ion. Sulfate ion starts off as SO4 2 minus and finishes as SO4 2 minus. It's what we refer to as a spectator ion. It's an ion that doesn't really take part in a chemical reaction. And therefore, for the purposes of this question, I can take it out to make this into an ionic equation, where you're only showing the ions that are actually changing. Which leaves me with magnesium plus copper 2 plus goes to magnesium 2 plus plus copper. Now we can go one step further and turn this ionic equation into two half equations. A half equation is when you're just looking at one element by itself. So if I take the magnesium first of all and make a half equation for it, magnesium is starting off as Mg and it's turning into Mg2 plus. And similarly, copper is turning off as copper 2 plus and it's turning into plain old copper. Now to show what's had to happen for those changes to take place, it's either going to have to have gained electrons or lost electrons for these two metals. If we look at magnesium, magnesium is starting off neutral and is turning into Mg2 plus. Basically it's become more positive. The reason it becomes more positive is because it's lost 2 electrons. So we'll put 2 electrons on the right hand side. That's now a balanced half equation. Conversely, if we look at the copper, it's starting off as copper 2 plus and it's becoming more negative. It's turning into copper. It's become more negative because it's gained 2 electrons. So plus 2e minus, that's a new half equation for copper. So using these two half equations, we have to evaluate why we've got a redox reaction, or why one's oxidation, one's reduction. If we look at magnesium, this equation shows us that magnesium has lost electrons. And we look back to our definitions, loss of electrons is oxidation. And if we look at the copper, copper has gained 2 electrons. And if we look at our definition, gain of electrons is reduction. So we would explain those 2 points in our answer, and then we look at the fact we've got an oxidation and reduction reaction happening in the same equation, and that therefore makes it a redox reaction because they're again both taking place at the same time. So we would explain that both oxidation and reduction are taking place, which therefore makes this a redox reaction. So now we move on to our second section in this topic, which is rusting. Rusting is probably something you're familiar with. It's the turning of iron into a compound which has that kind of red, brown, flaky structure to it. And first thing to cover is that rusting is an example of a corrosion reaction. Corrosion is basically anything that happens to a metal when it's left outside, when it reacts with like the air around it to go dull. So the proper definition of that is the reaction of any metal with oxygen, and so lots of metals will do that. If you leave them outside, they will go dull because they form an oxide layer. More specifically, rusting is a type of corrosion reaction that takes place for only iron. It will take place for steel as well. Steel is basically an alloy that contains 99% iron with a little bit of carbon, so it would rust as well, but just because it's got iron inside it. So rusting is a specific example of a corrosion reaction specific to iron or steel. Now there's a specific experiment you need to know about that proves the conditions you need for rusting to take place. Here's what it looks like. You start off with 3 test tubes, and into each you place an iron nail. In the first test tube, you'll just simply put water. In the second test tube, you'll put boiled water covered with a layer of oil. And in the third test tube, you've nothing apart from a little lump of powder of anhydrous calcium chloride, normally kind of suspended on 2 bits of cotton wool. And if we leave those 3 test tubes out for about a week, what we'll find is that the one on the left with water will rust, and the remaining 2 will not rust. and this gives us information about what we need for rusting to take place. So working backwards, the test tube on the right hand side contains anhydrous calcium chloride. Anhydrous calcium chloride is a drying agent, so it will remove any water vapour from the air. So all the air in this test tube is entirely dry and it's just got normal air in it and normal oxygen. So when you're just exposed to oxygen, you don't rust. In the second test tube, obviously we're exposed to water, but by boiling the water, we've removed any dissolved oxygen in that water. And the layer of oil on top prevents any oxygen dissolving back into the water. We don't get rust, which proves that if we just got water by itself without oxygen, we don't get rusting. The test tube on the left does have water, but water normally has got a little bit of dissolved oxygen in it, and we do find that this does cause rust. What this experiment proves is that for rusting to take place, you need both water and oxygen to be present. It's not enough just to have one by itself, you need both. The next thing which backs up that fact about water and oxygen being needed for rusting is the chemical equation for rusting. Rusting is essentially the reaction between iron, water and oxygen to make rust, and the proper chemical name for rust is hydrated iron 3 oxide. So if we look at the name for rust here, iron oxide implies that the iron has reacted with oxygen, hydrated means wet, which means you've got water involved as well. The specific way you need to describe the appearance of rust is as a red-brown flaky solid. The last thing we need to know about rust is methods of preventing it. And there are two main categories of methods we'll look at. The first one is the simplest method. This is known as a barrier method. A barrier method simply means that you're forming a barrier layer on top of the iron to prevent oxygen or water coming into contact with the iron. And if you prevent oxygen or water coming into contact with your iron, you're going to prevent rusting from taking place. To be more specific than just barrier methods, ways that which you would form that barrier could be by painting, using a plastic coating, or using a metal coating, or you could do oiling as well. The second method is a little bit more technical. It's known as sacrificial protection. Basically what happens here is we'll take our piece of iron we don't want to rust and we will attach a more reactive piece of metal to it, for example zinc or magnesium. And what will happen is that yes, water and oxygen can come into contact with the iron, but because we got a more reactive metal attached, the water and oxygen will react with the more reactive metal first, which protects the iron below it. So basically the more reactive metal sacrifices itself to prevent the iron from rusting. So the more reactive metal reacts with the iron first. One specific example of sacrificial protection is a method known as galvanizing, which when you coat your piece of iron in zinc, zinc's more reactive than iron, so therefore the zinc can sacrifice itself to prevent the iron from rusting. The last part of this topic is on iron itself. And more specifically, it's about how we would obtain iron from the earth. The reason that iron is so important is for its uses. It's a very strong, cheap metal, which is often used in structures like bridges due to its strength. Now, if we want to obtain iron, you cannot find iron found as the element in the earth crust. Iron is a reasonably reactive metal, so you'll find it already react with oxygen in the form of iron oxide. The iron oxide is normally contained within a certain type of rock, known as an ore, which is hematite. And our challenge is to try to get the iron out of the hematite to give us pure iron. So iron ore, whose proper name is hematite, contains iron oxide, and we're trying to get the iron out of the iron oxide. The formula of iron oxide is Fe2O3, so we're trying to remove just the iron from the oxygen. The method we use to take the iron out of the iron oxide is known as the blast furnace. The blast furnace is like a big factory where this process takes place. And we've got a number of reactions we need to know about to describe how that process works. So the blast furnace looks like a pretty large chamber where a number of chemical reactions take place. So this is a very simple diagram of your blast furnace. At the top of the blast furnace, we are going to place in 3 ingredients which are going to react together to produce our iron. The 3 ingredients are iron oxide, basically the iron ore, the hematite. The second ingredient is coke. Now coke is just an altered form of coal, it's carbon. And the final one is limestone, which has got its own use within the process. So at the top we're adding hematite, iron oxide, coke, which is carbon, and limestone, which is calcium carbonate. There are 5 chemical reactions you need to know off by heart which describe the process of the blast furnace. And I think the best place to start is actually in the third reaction, which describes the main purpose of the process. In the third reaction we see how the iron oxide, Fe2O3, loses the oxygen to leave us with just iron, which is the thing we're trying to make. The reactant that has taken the oxygen away is this chemical here, CO, which is carbon monoxide. Carbon monoxide removes the oxygen and turns itself into carbon dioxide, which obviously takes the oxygen away, allows us to make iron. The first 2 steps show us how we make the carbon monoxide, which will allow us to take the oxygen away from the iron. In the first step, the coke we put in at the top of the blast furnace, the carbon, reacts with oxygen to make carbon dioxide. In terms of where the oxygen is coming from, that comes from blasts of hot air down near the bottom of the furnace. That's where the blast furnace gets its name from, the blasts of hot air which provide oxygen for the first reaction. In the second step, the carbon dioxide we've made in step 1 comes down into step 2 and reacts with more coke, more carbon, and that converts the carbon dioxide into carbon monoxide. That carbon monoxide, once it's made, can feed into the third step and remove the oxygen from the iron oxide we've placed in at the top of the reaction. The molten iron produced at the end of this reaction is going to trickle down the sides and collect at the bottom of the blast furnace. This third reaction is a reduction reaction. It's a redox reaction, but it's reduction in terms of the iron. The iron is starting off with oxygen, is ending up with no oxygen. So for that purpose, or for that reason, the carbon monoxide is often referred to as a reducing agent because it is reducing the iron from iron oxide down into iron. Now step 4 and step 5 are 2 equations which show how we solve an issue we've got on the blast furnace. One problem with putting hematite iron ore in at the top is that it's basically a rock you've dug out of the ground. It contains iron oxide, but it's not completely pure iron oxide. Hematite also contains impurities, which are sometimes known as acidic impurities, more specifically silicon dioxide. Now what you would know silicon dioxide as is as sand, which is basically one of the main constituents of rock. So we need to get rid of the silicon dioxide because it's got a very high melting point. So any leftover silicon dioxide will build up around the blast furnace and basically clog it up. So we need a method of removing the extra impurities. It's actually the limestone we added in at the start which will help remove these impurities. In the first step here, in step 4 of that process, the calcium carbonate will break down due to the high temperatures of the blast furnace into calcium oxide plus carbon dioxide, and the calcium oxide from step 4 feeds into step 5 where it reacts with silicon dioxide, which is the acidic impurities from the hematite, basically the sand. That converts it into a chemical called calcium silicate, CaSiO3, which has a more common name, slag. The advantage of making this calcium silicate is that it's a liquid at the temperature of the blast furnace, whereas silicon dioxide is a solid. Because it's a liquid, it can flow down the sides of the blast furnace and collect at the bottom and be removed there. So at the bottom of the blast furnace, we're going to have 2 layers. The iron we made in step 3 has trickled down to the bottom, and the slag we made in step 5 has also trickled down to the bottom. The slag generally floats on top of the iron. The method we use to remove those 2 things from the blast furnace is known as tapping off. Basically, we open a big hole at the bottom of the blast furnace and the 2 liquids will drain off and we can collect them. So these 5 reactions describe the main steps in the blast furnace, which is the extraction of iron from iron oxide.